Hello, so in this video we're starting chapter 2 and we're starting with binomial expansions. So what is a binomial? Bi just means 2 and binomial would be anything with 2 terms. So something like 3y plus 2z, this has 2 terms, or 3y squared plus 3y, this has 2 terms, or 3y plus 2x, this has 2 terms. But something like 2x plus x, that is just 3x. So this is just one term. So this wouldn't be considered as a binomial. So now, usually what we like to think about is what happens when we try to expand 2 terms. So if we have a plus b, this is a binomial. So if I raise it to the 0 power, I get 1. And if I have a plus b to the first power, well, that is just a plus b. And I want to emphasize the coefficients. So that is 1a plus 1b. 1 times a is just a, 1 times b is just b. And what if I have a plus b squared? Well, that gives me 1a squared plus 2ab plus 1 times b squared. And up until this point, we have done nothing new. This is, I think, what is usually covered in 10th grade for Bhutan. And now what if I have a plus b cubed? I have, so well, that is 1a squared. That is going to be, well, a plus b squared times a plus b, right? That is a plus b cubed. And I know what a plus b squared is. That is just 1a squared plus 2ab plus 1b squared plus times a plus b. And if I multiply everything out, I get 1a cubed plus 2a squared b plus 1ab squared plus 1a squared b. So I multiply with everything with a first, like this. So I get, if I multiply a with 1a squared, I get 1a cubed. If I multiply a with 2ab, I get 2a squared b. And if I multiply a with 1b squared, I get 1ab squared. And now I do the same with b. So I start with here. So I get 1a squared b plus, and now you get the idea, 2ab squared plus 1b cubed. And if I combine everything, I get 1a cubed plus 2a squared b plus 1a squared b. That is 3a squared b. 2 apples plus 1 apple is 3 apples. 1ab squared plus 2ab squared, 3ab squared. And plus 1b cubed. So now what happens if I want to expand a plus b to the power 4? Well, now it's getting more and more difficult because I have more and more terms that I want to multiply and add out. So now let me give you another way to think about doing these expansions. So well, let me think. Suppose I have a plus b, 4, right? So that is just going to be a plus b times a plus b times a plus b times a plus b. That is what a plus b times to the power 4 means. And let me think of selections. So what are the different ways I can multiply things out? Well, I can pick a times a times a times a, right? So I can pick an a from all 4 of them. And I can say, well, hey, if I multiply those out, I get a to the power 4. Right? Or I could say, well, let me select a from my first term. And then I select a b from all other terms. So I get a from my first term and b from all other terms. So that is b cubed. But I can do the same thing. I can, instead of doing that, oh, I'm so sorry about that. Okay, let's keep things as they were. So instead of saying, hey, let me select a from my first term, let me select a from my second term, and I'll select b from all other terms. So that gives me another ab cubed. And I can do this with all my a's, right? I can pick an a from any term and then pick 3 b's from the remaining 3 terms. So that actually gives me 4 ways of selecting an a and b cubed. Plus, now what if I have selected an a from, I have selected 4 a's and there's only one way to do it. I have selected 1 a and then 3 b's. Now what if I want to select 2 a's? How would I do that? Well, I can select a from the first and a from the second, and then b from third and the fourth. That is one way. Another way is that I select A from the first and the third. Or another way is that and then again, if I select two A's, then automatically I'm selecting two B's, right, from the remaining two terms. So I can select from the first and the second, and then I can select from the first and the second. I can select A from the first and the second, or I can select A from the first and the third, or I can select A from the first and the fourth. So that is three ways. Or I can select A from the second and the third, or I can select A from the second and the fourth. That is two ways. Or I can select an A from the third and the fourth. So that is one way. And this adds up to 6 ways of selecting A squared, and automatically you select B squared. And if you use this thought process again, you see that, well, because it's symmetrical, right? You see that, hey, if I want to select one A, or if I just want to select one B, then there has to be the same number of possibilities. So we get 4. If I just select one B, then I have to select A cubed. So I'm going to get... And then if I just want to select a B from all the terms, I get B to the power 4. So that is another way to think about expanding binomials, selections. And because of selections, right? So we had 4 terms. So we were selecting out of 4, right? So if I selected an A from 1, I was selecting from the other 3, B from the other 3. So I am always selecting from 4. And this is what we call a binomial meal coefficient. And basically this formula gives us the numbers in front. So 1, 4, 6, 4, 1 is going to be given by this formula. Well, usually we were taking a specific example of 4, but we usually take it from n. And basically we're selecting k items, right? And what does this mean? Well, k is going to range from 0 to n. What do I mean by that? Well, I can select 0 A's. So we just think of one term here. We can just think in terms of one term. So if I just start thinking of A, right, I can select no A's. That is going to be B to the power 4 case. Or I can select 1 A and 3 B. That is going to be this case. Or I can select 2 A's and 2 B's. Or I can select 3 A's and 1 B. Or I can select 4 A's. So you can see that then K, which is the number of A's that I can select, or number of B's, it's symmetrical. This problem is symmetrical. So you can also think of the number of B's you want to select, but you don't want to do both of them because that would be double counting. So you would count everything twice, which is not what we want. So number of A's that I can select is going to be K. And the formula for this. Now, before we go to the formula for this, we want to discuss something about factorials. So basically, n factorial is given by n times n minus 1 times n minus 2 dot 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 times 1. So basically, 5 factorial, using this definition, is going to be 5 times 5 minus 1 is 4, times 5 minus 2 is 3, times 2, and I'm going to do this until I get to 1. And basically, this is going to give me 120, I believe. Right? And another important formula to know is that n factorial is going to be n times n minus 1 times n minus 2 all the way until 1. But based on the definition, from the second term onwards, we have n minus 1 factorial. Because this is just n minus 1, and then I'm taking 1 off, and then I'm taking 1 off. I do that until I get to 1. So n factorial is just n times n minus 1 factorial. And we can repeat this. We can write it as n times n minus 1 times n minus 2 factorial, and so on. So now that we know what factorials are, the formula for n choose k. So we say n, and then we're, out of n things, we're choosing k objects. Right? So that gives us n factorial divided by n minus k factorial times k factorial. So that is the formula. And an important thing to note is that 0 factorial is 1 and 1 factorial is 1. These are very important things to note. And that is it. That is everything that I need to say. But now let me give you another way to think of expansions and how you can expand terms. And that is by using something called Pascal's triangle. So let me erase everything. So you have learned how to expand using algebra, using the idea of selections. Now another way is to use something called Pascal's triangle. And basically, you are going to start with 1. And to construct this triangle, this is what you are going to do. You start with 1, and then you write 1, 1. So that is going to be, this is going to be n is row 1, and that corresponds to n is equal to 0. Row 2 corresponds to n is equal to 1. And row 3, you always start with 1. The middle, you're going to do 1 plus 1, that is 2. So that all the middle terms, the terms that are lower but then appear in between two terms, that's going to be the sum of the upper two terms on the sides. So 2 is going to be 1 plus 1. 1 plus 1 is going to give me 2, and then my edge is always going to be 1, my corner term. So I get 1, 1 plus 2 is going to give me 3 here, 2 plus 1 is going to give me 3 here, and then I get 1 again. And I keep on doing this. I get 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and I get 1. And I keep on going 1, 5, 10, 10, 5, 1. And I can go on and on. I can make this triangle bigger and bigger. But let's stop here for now. And this is going to be row 3, where n is equal to 2. This is row 4, where n is equal to 3. This is row 5, where n is equal to 4. And this is row 6, where n is equal to 5. Now, is there something that we noticed from our previous expansions? Well, if you go back to our video, if you rewind, and you notice that when we were discussing a plus b to the power 0, we got 1. When we discussed a plus b to the power 1, we got 1a plus 1b. And the coefficients are important here. A plus b squared was 1a squared plus 2ab plus 1b squared. And a plus b cubed was 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed, right? So let's look at the coefficients. I have 1, 1 and 1, 1, 2 and 1, 1, 3, 3 and 1. And that is exactly what we see here. 1, 2, 1, 1, 3, 3, 1. So if we have to use Pascal's triangle, so using this triangle, if I wanted to expand x plus y to the power 5, or a plus b to the power 5, then I'm going to start with 1, a to the power 5. And remember, if you look at everything that we have done, a starts to decrease. The power of a starts to decrease, and it decreases up until it gets to 0. And we were talking about what k was. K ranged from 0 to n. N is 5, so we have 5, 4, 3, 2, 1, and 0. Those are going to be the possible values of k, right? We start from 5, and then we use this as the coefficient. So row 6, n corresponds to 5. So we start with a plus b to the power 5. So I have 1a to the power 5, plus I'm going to have next is 5. A, the exponent, is going to decrease by 1. For b, it's going to increase by 1. So here we had b0, which is just 1. So b goes to 1, right? And then we have 10a cubed b squared. 10a squared b cubed. 5a b cubed, or b to the power 4. And finally, b to the power 5. We have 1 in front. So that is how you're going to expand. So this is how you can use Pascal's triangle to do a binomial expansion. And we were talking about this. Well, we said that each coefficient can be given by, is actually known as binomial coefficient. So it's related to what we were doing before. It's related to n choose k. And how is it related? Well, let me show you. Let me show you for this example. So if n is 5 and I start with 0, that is 5 factorial divided by 5 minus 0 factorial times 0 factorial. And that is just going to give you 1. 1 is 5 factorial times 4 factorial times 1 factorial, that is just 5. And 2 is just 5 factorial divided by 3 factorial times 2 factorial. That is just going to be 10. And if you perform this up until, 5, 5, you get back to 1. So you start with 1, you get back to 1. And these numbers are the same numbers in the triangle. 1, 5, 10, 10, 5, 1. So that is what you are going to get. So you can see why I introduced this idea and how it's related to your coefficients and the Pascal's triangle. So now you can also say that for each row, I have my numbers, the coefficients are going to be n choose k for k less than or equal to n and greater than or equal to 0. And k is an integer. A k is an integer with 0, right? Yeah, k is going to be an integer. K is an element of 0, 1, and going to go until n. So these are the possible values of k that you have. So now that we have connected Pascal's triangle to selections and binomial coefficients, let's look at some patterns that arise in the Pascal's triangle. So let's look at, say, the sum of each row. So sum of 1 is just 1. The sum of row 2 is just 2. The sum of row 3 is going to be 4. The sum of row 4 is going to be 8. The sum of row 5 is going to be 16. And the sum of row 6 is going to be 32. And if you notice, if I relate to the powers of n, to the number n, then, well, the sum is just 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and therefore, for the any n value, the sum is going to be 2 to the power n. And let's think, why is that so? Well, we have discussed, if you're expanding a plus b to the nth power, right, we have, so we're going to start with, now I'm going to, instead of writing it as numbers, right, instead of writing it as numbers from the Pascal's triangle, let's use the idea of binomial coefficients. Well, I told you we're going to, it's always going to have n, right? We're always going to be selecting from n things. Always going to be selecting from n things. And we said that our k is going to start from 0 and increase all the way up until n. So we have nc0, and we said, hey, my a is going to start from the highest power, and my b is going to start from 0. My a now decreases by 1, b increases by 1, and so on. A decreases by 1 again, b increases by 1 again, up until I have no a's and I have just b to the power n. So that is what and this is your binomial expansion formula. So this is a very important formula, and I was planning to introduce it just during the next section, but now that I've already done it, this is a formula that you want to learn. This is the formula to go to when you're expanding. So Pascal's triangle is useful when you're expanding up until, say, n is equal to 5 or 6, but if it's n is equal to 16 or n is equal to 30 or a big number, then you want to use the binomial formula. Well, let's say if I put now all these numbers in the row, they are just the binomial coefficients, right? That's what we have been talking about. They're just these values, the n1, n0, n1, n2, n3. Those are the coefficients. And we want to know what the sum of those coefficients are. So I would have to assume that if my a is 1 and b is 1, then I get n0, and this is just 1, and I have n1, and this is just 1 because 1 times 1 is just 1, n2, on and on until nn. So you can see that 2 to the power n is just the sum of the coefficients. So you can see why when we added everything in a row, we got 2 to the power n. And although you haven't learned this yet, one way to represent this is in this way. But you don't have to worry about it. This is just telling me that 2 to the power n is going to be the sum of my binomial coefficients with k, and then my k starts from 0 and it goes up till n. That is just what it's saying. And sigma just means you're adding sum. So this just means that you're adding 1 plus n 0, because you're starting from 0 and you're going all the way until n, because that is where your k ends. And that is it. So you know what the sum of each row is for a binomial, for Pascal's triangle. Let's see if we can figure out any other patterns. Because Pascal's triangle is full of patterns, right? So now let's take this diagonal. And you might be wondering, well, what's so special about this diagonal? Well, this diagonal gives us triangular numbers. And what are triangular numbers? Well, those are 1, 3, 6, 10. And basically, if I take one dot, I can make it, this is like the 0th triangle. And if I take 3 dots, I can make a triangle. If I take 6 dots, I can make a triangle. And if I take 10 dots, I can make a triangle, right? So that is why these are called triangular numbers. So now for my triangular numbers, right? And let's think about k, because I told you for every row, k starts from 0 and goes up to n. It starts from 0, goes up to 1 when n is equal to 1. It starts from 0, goes up to 2 when n is equal to 2. It starts from 0 and goes up to n when 3 when n is equal to 3, and so on. So these are not powers, right? These are just my values of k. So please remember that. These, do not confuse them with exponents. So I'm just saying that my k value, right, starts from 0, 1, 2, 3, and goes until it matches n. So if you notice that for triangular numbers, your k is always going to be 2. So that is something to remember. And I said every term just is just n choose k, and k is going to be 2 here. So this gives me n factorial over n minus 2 factorial times 2 factorial. So that is just n factorial, n times n minus 1 times n minus 2 factorial, based on the formula we discussed, n minus 2 factorial divided by 2. And that is just, these cancel out, so you get n minus 1 divided by 2. Right. And if you start from n greater than or equal to 2, well, if you substitute n is equal to 2, then you get 1. That is your first triangular number. If you put n is equal to 3, you get 3, I believe, because this is going to be 3, this is going to be 2, 2 divided by 2 is just 1, so you get 3. If you put n is equal to 4, you get 6. So this gives you triangular. So n2 gives you the first triangular number, n3 gives you the second triangular number, and 4 gives you the third triangular number, and so on. So because k is 2 and the binomial coefficient gives this formula, which represents the triangular numbers for n greater than or equal to 2. So that is why that diagonal with k2 gives you the triangular numbers. Now let's notice something else. Now that we know that the diagonal where k is equal to 2 is equal to triangular numbers, well, let's add consecutive triangular numbers. If I add the first two triangular numbers, I get 4. If I add the second two triangular numbers, I get 9. If I add the third, if I add the second and the third, if I add the third and the fourth triangular numbers, I get 16. And my first triangular number is 1. So that is 1 squared plus 1 squared, 2 squared. So I'm just looking at the numbers. So that is 3 squared and that is 4 squared. So it seems that like the sum of two consecutive triangular numbers is always a square number. So let's try to prove that. So we said that a triangular number can be represented as n times n minus 1 over 2, right? So that was for n greater than or equal to 2. Remember that. This is the condition. And then, well, this is going to be our starting triangular number. So what's the next triangular number? Well, it's going to be n plus 1, right? And then I have n plus 1 minus 1. So that is just n divided by 2. And if I add these up, I see that I get n squared for n greater than or equal to 2. So the sum of the first two triangular numbers in my diagonal is going to be 4 because it's 2 squared. The sum of the next two is going to be, I put n is equal to 3, I get 3 squared is 9, and so on. So you see why the sum of two consecutive triangular numbers is going to give you a square number. And you can see that from Pascal's triangle. And the last pattern that I want to show you is actually the Fibonacci sequence. So the Fibonacci sequence is a sequence of numbers that follows the pattern fn plus 2 is equal to fn plus 1 plus fn. And that just means that for n greater than or equal to 1, right? So that just means that f3 is equal to f2 plus f1. f4 is equal to f3 plus f2. And so on. And basically what I'm saying is my My third term has to be the sum of the second and the first. So my third term has to be the sum of the first and the second. So this is the Fibonacci number. So it's 1, 1. 1 plus 1 gives me the next number is 2. 1 plus 2 gives me the next number is 3. 2 plus 3 is going to give me 5. So can we try to spot this sequence? The next number is going to be 8, by the way. Can we try to spot this sequence in our Pascal's triangle? Well, now if you remember the idea that you got from grade 10 chemistry, which was the snake diagram, if you look here, this gives me 1. If I do this, this gives me 1. My next diagonal gives me 1 plus 1 is 2. And the next diagonal is 2 plus 1 is 3. And the next diagonal, like this. So my k values have to decrease. I start with 2, I go to 1, I go to 0. So 1 plus 3, 1, 3, 1, that gives me 5. So that's how you get the Fibonacci sequence. So that is some of the beauty in patterns, because you can see that a simple triangle that was constructed using such a simple rule has so many hidden patterns and rules behind them. The sum of each row is 2 to the power n. You see that there are triangular numbers. You see that there are square numbers hidden there. The Fibonacci sequence comes from the Pascal's triangle. So these are just very cool things about the Pascal triangle. And these are going to be very helpful. Knowing this triangle is going to be very helpful to solve some of the questions related to binomial expansion. So in the next video, we'll start solving questions from the first topic. And yeah, see you in the next video.